Okay, now in terms of homeworks also, your homework for this week is going to be perhaps the last large homework. You have about 7 problems, which may take some time to solve. But this is really the last of the fundamentals problems. I mean, you're going to have, of course, more problems later, but they're going to be less problems and more applied character. There is one interesting problem again from Izrevashvili, which we may discuss in the lectures, of the non-trivial type. But apart from that, it's, I mean, you have to do this homework. Now, because we have the test on Thursday, I put the deadline for the homework on Tuesday, so you can kind of think about the homework, and whatever comes across the homework, you can come on and task on Thursday or on Tuesday during the office hours, and of course Daniel and Angelica can help you too. So this is about the test. Again, the material that will be included is up to the next lecture. Now, of course, I don't want you to think about the test now. I want you to think about the lecture and how we're going to use colloidal manipulation by using electrical fields. So that's what we're going to speak about today. So far we know, I believe, everything that you have to know on this kind of like this introductory stage for colloidal suspensions. You know everything about interactions between particles, cylinders, thin films with flat surfaces, a few things about biological molecules and so on. Now, what we have to finish off, and that's important in colloidal engineering, is how we can use electrical fields to manipulate particles, external fields. And in the next 2 lectures, we're going to study the fundamentals of using external fields to manipulate colloidal suspensions. And this is by no means a new area, but it's getting very important now because you want to really use these fields as a means of assembling new types of structures, new type of devices. Furthermore, it's getting to be more important because, again, electronics and semiconductor materials are really getting to be out of the solid state semiconductor domain. They're really spreading out. They're interfacing colloidal suspensions. So you want to know how to use different electrical fields in order to use electrical circuits, for example, to manipulate the particles. So this time we're going to, in this lecture today, we're going to study the fundamentals of using constant electrical fields to manipulate particles. And in the next lecture, we're going to study the fundamentals of using alternating electrical fields to manipulate particles. And by the end of this week, you're going to know the fundamentals of using fields. And this more or less concludes the strictly fundamental lectures of this course. Of course, before we start, some inspirational, interesting image. And it relates to what I have been telling you about using electrical fields to manipulate colloidal objects. Now, in this case, the colloidal objects are also of very significant importance. This is DNA fragments. There is a company called Nanogen, and we're going to learn about the techniques that are used by this company to make biological chips a bit later, which makes chips where you can eventually study the existence of certain fragments, DNA fragments in your sample. So, I mean, check for diseases, whatever, genetic information, and so on. Now, if you remember in the previous lecture, I was telling you that DNA can bind even if there is a mismatch in the 2 chains. However, the difference between the case of match and mismatch is significant, and it is in terms of what? Energy of binding. If there is a mismatch, the binding will be weak compared to the case when everything matches perfectly. The question, however, is that if you just have DNA binding on chips, which most of the people in biology do, you can hardly distinguish between perfectly matched and slightly mismatched pairs. So what this company has developed is this technique where you can distinguish the strength of matching by using electrical fields. First, you can use electrical fields to attach the DNA, and then you can use the electrical fields which actually repel the DNA fragments which bound to the chip. And in this way, if they are not bound really well, they're going to get eventually separated and will fall away. So this is an example of how you have a chip before using the electrical circuit, and you have a chip after the after using the electrical. It's called electronic stringency test. So you can see that although DNA matched on all samples originally, after you apply the field, there are only a few areas which remained fluorescent. This means that the DNA fragments kind of separated from the chip, and something like that you have in this case too. So right now our task in this class today is to understand why DNA moves under electrical field and what happens when you apply the electrical field to colloidal suspension. And let's start here with some question for discussion. Now we have very simple system, a colloidal particle, let's say it's negatively charged in water, which means that it has counter-ionic atmosphere. And then we put this between two electrodes and apply constant electrical field, plus minus. Now what should happen here, if anything? And if it happens, what exactly will happen? Is the particle going to move left or right, for example? Now, just to confuse you a little bit, now I'm going to confuse you now and you tell me the right answer. To confuse you, I'm going to tell you like that now. This is a particle which is negatively charged, but then we have counter-ionic atmosphere which is positively charged. So the whole kind of, let's say, complex particle and counter-ionic atmosphere is on average charged what? It's charged neutral. So then should it move in the field at all or not? And then if it moves in the field, is the field going to interact with the counter-ionic atmosphere, or is the field going to interact with the charge on the particle? Now what's going to happen? So in which direction it is going to move if it moves? So any suggestions here, kind of like, let's see hypothesis, and I'll tell what is right, of course, right now. What?
Left.
Left. You said it's going to move left. Well, okay. Any other suggestions? Now, why would it move? Okay. Okay. Well, you can say right, of course. Now, let's start with the motivation why it should move right. You can perhaps say that, the charges which are on the outside are positive, so it should move towards the negatively charged electrode. Now then, what's the motivation for moving left? Why should it move left?
It would separate the two, it's like polarization.
Yeah, it's kind of, this is the true answer. So the true answer is that it's going to move left. And the reason it's going to move left is that the particle has a large negative charge and you have small positive charges in the counter ions. When it gets polarized, the counter ions are going to separate from the particle. So the particle itself is going to get kind of like a little bit naked out of the counter ions and is going to move left. Now, however, the explanation is not quite precise. And the reason is like that. Now you can say there is a polarization. Let me kind of torture you a little bit here. You can say there is a polarization, but this is also the equivalent of a dipole which faces the other way. So when it gets polarized, a dipole in itself is not going to move in the field, in a homogeneous field. What is the reason then it can move? There is a little bit of trickiness here. Let me tell you the answer. Now, if it's in ionic environment, you're going to have positive and negative ions around the particle, right? So if the positive ion starts moving right and the particle itself starts moving left, there is going to be a dipole, but this dipole is not going to really remain permanent in the sense that positive ions are going to come here and move further on. So it's really the particles are going to move against the ions, and the ions are really going to be on the other side, so it's always going to keep moving in the field. And it's always to be kind of stripped of most of the counter ions, which are going to be trailing behind and moving towards the other electrode. If the particle was not stripped of the counter ion, it is not going to move. If you have a particle which is charged and all the ions are, let's say, attached to the particles, if you take nails and nail the charges down, in a way, the particle is not going to move at all. And as we're going to see, actually, we always have charges which are constantly on the surface of the particle. Not all the charges move together with the particle in the opposite direction. And we have to take into account this when the particle starts moving. Okay, any questions here? Did you get confused well enough, or shall we kind of try to address this in formulas now, or you would like to ask something?
So if the particle is neutral, it won't move. That's the one reason.
No, the right answer is if the particles cannot separate a little bit from the counter ions, it's not going to move. If the counter ions, or let's say, imagine that the counter ions are kind of bound to the surface of the particles in a strong manner, then it's not going to move. The reason that particle move is that the counter ions can be displaced. And so not all, only some of the counter ions can be displaced from the surface of the particle.
Is that the same thing as having a neutral particle?
From the viewpoint of electrophoresis, if the counter ions don't get displaced from the particles, then you're going to have a neutral particle.
Is that what you were asking, Raj?
Yeah, that's what.
Right. For example, let's say if you make a gel particle and kind of you incorporate the counter ions in the gel, it's not going to move. The only reason anything moves is that because the counter ions get displaced. And we're going to address this in a little bit of a theory right now. First, we have to discuss the reasons for the mobility and just make a very simple balance. Now, any chemical engineer would know that, but we have other people in this class. Now, this is a very well-known formula, right, which gives you the mobility, what is the mobility of a particle in viscous liquid as a function of the force applied on the particle. If we put here gravitational force, this formula is going to give you the speed at which, let's say, a sphere sediments down towards the bottom of the cylinder. And you have this 6 times P, ether is the viscosity of the liquid, and R is the radius of the particles. Now, on the other hand, of course, electrical engineers know that better, but I mean, you should remember from the first part of the class that the force on a charge is equal to the charge times the intensity of the field, times the field. So we have the two forces here which operate on the particle. One is the force, viscous force of friction with the liquid. The higher the viscosity of the liquid, the higher the friction force. This friction force is balanced with the electrostatic force. So then if we balance the two forces, kind of cancel out the forces, we have this formula for the velocity of the particle as a function of the of the field. So the velocity is going to be equal to the charge of the particles divided by this factor, which is the hydrodynamic resistance, times the field, the electrical field. And now we can bundle everything in a parameter which is called electrophoretic mobility, U. And this parameter is going to be the velocity of the particle divided by the field intensity. Now, it has a relatively unpleasant dimensionality, meter squared divided by volts times second. So anytime you have to do calculations, you have to be careful about the dimensions of the dimensionality of the electrophoretic mobility. But on the other hand, the electrophoretic mobility is the one that you measure experimentally. Experimentally, you apply a field, you see the particle moving, you measure the velocity, and you know the strength of the field, how many volts you applied to the electrodes. So this is the thing that you can measure, you can see macroscopically what happens. And we're going to relate this to the charge of the real charge of the particle and the ionic concentration and so on further in the lecture. Any questions so far? Okay. One point further out. Now we have to, so far we have seen the particle, it moves, we know that it moves, that's great. Now the question is, okay, now what is actually happening? How do the ions move around the particle? And I'm not going to go into too many details about electrochemistry here. I'm just going to give you the basics of what happens to the counter ions and how do you attribute different properties. Now, first of all, you have a charged solid surface. What you're going to have against the charged solid surface, now this surface is obviously going to be positively charged here. You're going to have some counter ions which are just opposite to the charges. And it's also likely to be hydrated. So some counter ions are going to be just right next to the surface. And then you're going to have, like this diffuse counter-ionic atmosphere, these ions whose concentration decreases exponentially. And you know what is the exponential, what is the measure of the exponential decay here? Counter-ionic atmosphere, the bilent. So you're going to have a layer of ions which are right next to the surface. You're going to have some ions which are not that strongly bound, a little bit further out, and then you're going to have ions which kind of are attracted, but not that dense, further out and out. Now, it is usually assumed, and quite physically correct, that the first layer of ions is actually really tightly bound to the surface of the particle. So you can think of as an immobilized layer of ions, and this is called the so-called Stern layer. Now, you can think of what happens here as a kind of a capacitor. You have positive charge here and negative charge here. Electrochemists like to describe this as a kind of a capacitor, and that is actually, you can measure the capacitance of an electrode. So in order to describe a capacitor, you also need some distance which describes the distance between the two plates of the capacitor. So this capacitor model is called Helmholtz model. And the distance between the surface and the counter plane of the capacitor is called Helmholtz plane. Now, Helmholtz plane is a kind of physical approximation. Of course, you don't have a plane really existing there. This is just you ascribe this plane in terms of electrical properties of the surface. And then, if you have hydrodynamics, like the particle moves in the liquid, right? You have hydrodynamics, and this hydrodynamics is going to exhibit drag on the particle. And it exhibits drags on the particle because the hydrodynamic velocity on the surface of the particle is what? No. What is the velocity of the liquid with respect to the surface of the particle? It's Okay, actually you're right that it's velocity of the particle. The relative velocity of the liquid on the surface is 0. So there is no slip condition on the surface of the particle. The liquid cannot move at where it meets the particle. Now you know that it's going to move in the bulk, or the particle is going to move with respect to the liquid. The point is that, as you know, you have these boundary layers, and in order to describe different hydrodynamic systems, you would like to say, okay, now let's say the velocity of the liquid, which is likely to be something like, let's say, like this is 0. So it kind of, it moves very little here, and then it starts moving up. You can ascribe the velocity of the liquid actually as being 0 to a slip plane, and then being equal to the velocity in the bulk. Okay, that should be horizontal here, being to velocity of the bulk outside of this slip plane. Now, how exactly you define this slip plane is a tough question, but you can always say, okay, I mean, that's my model. And then if you consider the ions, now the ions which are between the slip plane and the surface are going to be what? Immobile. The ions that are going to be here after the slip plane are going to move with the liquid. This means that the moment the particle starts moving, you're going to have the ions which are here are going to move, and you're going to get stripped of the particle. And the ions that are here are going to stay together with the particle. These are the ions that I was kind of describing as being nailed down on the surface. So the particle is going to move together with some of the ions, and then at a distance further out than the slip plane, the ions are going to get stripped out. So when you speak about the potential of the plane, you can have a potential here at the shear plane, the slip plane, and this potential is called zeta potential. It's the most important parameter that we're going to discuss starting from the next slide. But here I want you to understand physically what happens and how do we model that, and it's a good model. The question where is exactly is the shear plane? It's a tough question. I mean, it's difficult to solve theoretically. You can measure it experimentally though. The point is that whatever is after this distance apart is going to move away, and you're going to have the potential that matters is the potential in this plane, because everything else moves together with the particle. Okay, questions? Sorry?
Which point?
The shear plane or slip plane here. So this is the one that's important. This is the plane which generates electrical properties. If this plane was at infinity, the particle is going to be electroneutral. Kind of the particle moves together with all the ions that are in this layer, and all other ions that are here are shear. So then the charge of the particle is going to be the charge here of the surface minus the charge of the counter ions which are in this layer. So kind of eventually when you apply the voltage and the particle starts moving, the charge that you're going to see is the charge of the particle plus the charge of all the ions which go together with the particle between the shear plane or the slip plane and the surface. So this is the effective charge of the particle, and the potential which is generated by this plane is called zeta potential. And we'll see how we're going to describe it right now. But this is the potential that you measure. This is the one that your equipment is going to register. You can have 1 ion per, let's say, square angstrom, or you can have 10 ions here. You don't know that, and you cannot measure that. From the viewpoint of your system, whatever is here is a part of the particle. Whatever is out here is the counter-ionic atmosphere that matters in electrophoretic mobility. Again, this is a very important concept, so if you have questions, now is the time to ask. From here on, I mean, you just have to describe this theoretically and obtain very simple formula. Again, there is some hydrodynamic shear plane which shears the ions. Now, the ions which are between this plane and the particles are effectively immobile. They move together with the particle. So the charge on the surface of the particle does not matter. The charge that matters is the charge of the surface of the particle plus all the ions that go together, that move together with it through the suspension. This is the one that you measure experimentally, and this is the one that measures for the mobility of that matters for the mobility of the particle. Okay, let's describe this theoretically then. You have, let's say, the true radius of the particle and the radius of the particle plus the radius of the stagnant hydrodynamic layer, so the radius until the shear plane. Obviously, this radius, r prime here, is a little bit larger than the radius of the particle. You have the surface charge of the particle and you have the effective charge of the particle together with the counter-ionic atmosphere. You have the true, that shouldn't go through the symbol. You have the true surface potential of the particle, and you have the potential in the shear plane, which is the zeta potential, and which is the one that actually kind of comes forward for you to measure and to register. So when we have been describing particle-particle interactions, we have been using the true potential on the surface. For the case of electrophoretic mobility, however, when it moves together with a counter-ionic atmosphere, we are using the zeta potential, which is the potential at the shear plane. Because in this case, some of the ions move together with the particle. And then we have derived this formula, I think, but it's not even really important. I mean, this is basic physics formula. This is the potential distribution around a charged sphere. Charge of the sphere, radio coordinate, radius of the radius of the sphere. Now we can say, okay, now can I define the potential in the shear plane? Why don't I replace the radial coordinate here with the coordinate of the shear plane? Replace the true charge of the particles with the charge again in the shear plane. And because r and r prime are very close, we can assume that r and r prime are the same. So then these two terms cancel each other. And we have this important definition of the zeta potential. Which is the potential in the shear plane, which is equal to 1 over all those parameters, which are fairly familiar, plus 1 times kappa r times the effective charge of the particle divided by the effective radius of the particle. Now the immediate question would be, okay, this is just, just plug in some effective parameters in the formula, but we don't know exactly the meaning of r prime and how large it is, right? However, now see what happens. We already derived this expression for the electrophoretic mobility. Okay, this wouldn't write now. It's kind of, this is a whiteboard with a character. So we already had derived this expression for the electrophoretic mobility. We have this expression for the zeta potential. Now q prime over r prime, can be substituted, and this can be in the case where this one is small, which means small sphere. Then we have this expression which relates the electrophoretic mobility, the zeta potential, the viscosity, and this is just the dielectric permittivity of the media. And now what is the importance of this expression? This is the basic expression which all instruments for measuring electrophoretic mobility use. With some, we're going to see some additional corrections. But let's say this is the simplest expression. If you take a particle and if you apply a certain field, you can measure the velocity of the particle. When you divide the velocity by the field, you're getting the mobility, which is the experimental parameter. From this mobility, just by knowing the viscosity of the liquid and the electric constant, you can measure the zeta potential. Calculate it actually. And the zeta potential is the closest thing that you can have to the surface potential of the particle. It's very tough to measure surface potential of the particle, but it's relatively easy to measure zeta potential of the particle. So if you have a suspension of unknown particles, you put them in the field, measure how fast they moved, you determine the zeta potential, and you have an approximation about the potential, how charged these particles are. Okay, could you follow everything here? Questions? Comments? Okay, okay.
Is there a sign error?
Ramos first, huh?
Is there a sign error in the potential expression?
Zero sign, sorry?
In the very first psi of r?
Here.
Yeah.
Uh-huh.
I don't know how you get rid of the two exponential terms unless there's a sign difference.
You mean here, how you get rid of two exponential terms. Now, now the shear plane is usually very, I mean, like in real measurements, it's a few nanometers away from the surface.
Mm-hmm.
A few ionic diameters. Which means that r and r prime are approximately the same. Oh, okay, sorry, this one should be plus.
Okay, that's all.
Excuse me. One of those is plus. So r and r prime are essentially the same. So that's how they cancel.
Got it.
Yeah. Okay. That was it? Okay. Yeah, Daniel had a question.
You probably said this earlier, but this is kappa r prime less than 1, I guess means that the Debye length is a lot bigger than r prime, right?
Well, yeah, I mean, people would like to use this because it's a dimensionless expression.
Sure, but I mean, it's like saying that this is true under these conditions.
Right.
These assumptions.
Right.
And I'm just wondering why is that so?
Because so in this case you can just cancel out this term and you have this simple expression.
Yeah,
But then okay, but
perspective.
physically okay, this is a good question for the next slides.
Okay.
Now, so we derived the expression. Now what we did, we derived the expression for kappa r. Okay, suddenly this started working. It stopped again, started again. Okay, fine. So we derived the expression for kappa r much smaller than unity, which means very small particle compared to the length of the counterionic atmosphere. Or essentially, physically, very small particle. Small spherical particle. Now what we're going to do immediately right now in the next slide, few slides, we're going to derive the expression for the other case. Now what happens if we have a essentially infinitely large particle, flat surface? And in order to study this system, I mean, you can do something very simple. You can take two electrodes, put them in a capillary, apply a voltage, and what you're going to find out is that the liquid starts moving. And this effect is called electroosmosis. It's a very important effect, especially for pumping in microfluidic devices and microchips. So we're going to study it specifically for the case of microfluidics later. Right now, from our viewpoint, you can think of this case as having some infinitely large surface without any significant curvature, because the curvature of the capillary here is enormous on the colloidal scale. It's essentially a flat surface. And then if we know the velocity of the liquid, we can get an expression for the, again, the relation between the surface, the zeta potential and the mobility. So in the first case, we had a particle moving with respect to the liquid. Now we have liquid moving with respect to the walls of the liquid. But the effect is essentially the same. The effect is that when you have ions, they move, and the charge on the surface, in this case, stays constant. In the other case, so in the first case, the particles move, the ions stay. In this case, the ions move, the capillary stays. But the effect is essentially the same. It's related to the surface charge. So what you can do is you can do a balance of the forces here. You have to do a balance of the hydrodynamic forces, which would be equal to the electrostatic forces. Now, the electrostatic forces which operate on a volume of a liquid are equal to, of course, you have field times charge. Now, field times charge is equal to the charge in a volume of liquid, infinitely small volume of liquid, is the density of the ions times the surface area times this distance between the two surfaces of this small thin volume of liquid, which moves a little bit away from the surface. So this is the electrostatic force which pulls, let's say, this liquid in one direction. Now this force is balanced by the hydrodynamic force. Now the hydrodynamic force is equal to the viscosity times the gradient of the velocity times the area on which it works. Viscosity times the area times the gradient of the velocity gives you hydrodynamic force. Now, there is a hydrodynamic dissipation on this side of the volume, and there is a hydrodynamic dissipation on that side of the volume. The hydrodynamic force which operates inside the volume is equal to the essentially when you subtract the force working on this side minus the force working on that side. So the difference between two forces is equal to the force which pulls the liquid charges in a certain direction. And these two terms essentially gives you the second derivative of the velocity. So we have this simple equation which gives you the electrostatic force working on a volume of a liquid close to the capillary wall, and the hydrodynamic force, viscous force, which works in the other direction, which essentially does not allow the liquid to move. So electrostatic force pulls all the ions together with the liquid in one direction. The viscous force works in the other direction to keep the liquid immobile, because, of course, when the liquid has viscosity, it doesn't want to move. This is just an example of what happens actually, why this is a bit complex equation. The liquid velocity away from the wall changes from 0 to some constant velocity far away from the wall. The electrostatic potential increases actually, decreases away from the wall. So the wall is charged, and the potential, this is actually a decrease of the potential. The zero potential will be here. So the velocity increases, the potential decreases. And in the next slide, I have actually done the integration schematically. If you like integral and differential calculus, you can follow this derivation. These are the boundary conditions here explaining the case. So we take this equation. First, we integrate it once with respect to the distance, again, away from the wall. Take into account the boundary condition, integrate it a second time. And when we're done with all those integrations, we obtain this very basic equation for the mobility of the liquid inside the capillary. The velocity of the liquid inside the capillary divided by the field which, if we remember, was the one which we denoted as electrophoretic mobility, is equal to the electric permittivity times the zeta potential divided by the viscosity. Now, tell me what this formula reminds you of, and then tell me if you have any questions, of course. Let's start with questions. I hope you're not trying to integrate the equations on your own there. Okay, let's think about your questions. Let me tell like that now. We derived the formula for the mobility of a sphere in the field, assuming that the sphere is very small, very curved. Next, we derived a formula for the mobility of the liquid inside the capillary, a charged capillary, and the direction of the field. So in this sense, the liquid moves, but we have some enormous particle which stays constant, for example. And then if we compare these two formulas, which I have done on the next slide, this is the formula which we derived for surface, which is called Helmholtz-Mulhovsky equation. And this is the formula which we derived for a sphere, which is called Huckel equation. They were just derived by two different groups of researchers studying different phenomena. And finally, when they did that, they realized that actually it's the same phenomena. This is charge mobility in colloidal systems. And then a researcher named Henry kind of noted that these are the same equations with a different factor here. And actually, because we derived this equation in lots of approximations, if you take the real case, this factor is going to be actually variable as a function of the counter-ionic atmosphere, the radius of the particle or the capillary, and the potential. So actually, people have done lots of heavy theory in order to tabulate these factors and give you this factor for the whole region between kappa r much larger than unity and kappa r much smaller than unity. So whatever type of colloidal system you have, small particle, intermediate particle, large particle, flat surface, what you do is you start with the Henry equation. You just have to go and find in the textbook the right factor. You plug it in here. Let's say you have 50 volts at kappa r equal to this case. So you know kappa r, you know what the factor is. You put it in the formula. You can measure the mobility of the particle and you get the zeta potential and vice versa. So this is the basics of all electrophoretic measurements. This is the basics of all the instruments which measure surface potential of the particle. And tonight now you know that you don't measure surface potential, but you measure zeta potential, which is a little bit lower or higher than the surface potential. Lower, obviously. So this is kind of, electrophoresis 101. We're going to study some applications now. But again, like this is important, so any questions are welcome now.
What exactly is C?
This case, it's essentially, now I have taken this from, I have used this F as a factor. Now C is this factor F, but just this is because it's taken from another book.
Okay.
Now, this is taken from Evans and Wennerstrom. And if you read it carefully, you'll find out that actually they have an error in the factor there. They have put the factor as 3/3 or something like that, 3 seconds. So you have to be careful because these are, you have a million factors and people make mistakes, of course, like I do in the lectures sometimes. Of course, if you have to do real measurements, you're likely to buy equipment which comes with its program. Now, the fact that some clever programmer has done the programming for measuring the electrophoretic mobility does not assure you that you're measuring the right potential, and we're going to discuss this a little bit later. There are lots of errors that can be made in such measurements. But the basics of this is all the same. You measure how fast it moves per certain field, and from there on, knowing the viscosity and knowing the electric permittivity, you can immediately find out what the potential on the surface is, knowing that this is not the true potential, but this is an approximation of the true potential close to the surface. Any other questions here? Yes, Yushin?
What type of radius is used for printing?
What type of radius? You mean in the kappa r? Usually, like I told you, the shear plane is only a few nanometers away from the surface. So you can just use the radius of the particle or the capillary that you know. You don't have to correct the radius for the shear plane. In the case in this case, kappa r this is the radius of the sphere. In this case, this is the radius of the capillary, but it's so large that it's essentially insignificantly small. So what you're going to solve, that you don't have to correct the radius for the shear plane, if that's your question. You just take the radius of the particle or your system, characteristic curvature. Okay, so you are probably not going to use this directly, but let's go back to this experiment. And this is important. We apply voltage. You can think of the capillary as being a very large particle moving with respect to the liquid, but actually the liquid is the one that moves with respect to the capillary. The point, however, is that this liquid moves, and then this is very important, especially these days when you have microchips for moving liquids. So you want to elaborate a little bit further on how this liquid moves inside the capillary. And you know that when the liquid moves inside the capillary by hydrostatic pressure, it moves by parabolic flow. In this case, however, what makes the liquid moves is the surface charges here on the wall of the capillary. So what drives the mobility is the surface charge of the capillary. There is nothing that drives the mobility here when it's away from the walls. So in this case, the hydrodynamic profile is not parabolic. It is called plug flow. What happens is that the liquid here moves with constant velocity, but for the case for the walls, where you can assume that there is this slip case where, it just decreases from the value in the middle to this value here. And now you want to calculate what this plug flow is, what the rate of this plug flow is. The velocity divided by the potential is equal to, like as we described, the Helmholtz-Minkowski equation, Z the potential of the capillary, divided by the viscosity of the liquid. So the more charged the capillary, the faster the liquid is going to move. Now, we can say that the macroscopic velocity of the liquid is going to be, because this is, you see, this is a plug flow, so the velocity is more or less the same, except very close to the walls. It's equal to the cross-section of the capillary times the velocity here in the middle. And then you can put in this value of the velocity here. So you have the relation between the macroscopic velocity of the liquid, the potential, the Z potential of the wall, the field, and the intensity. So this is the formula which tells you how fast the liquid is going to move as a function of the electric field that you apply. This tells you, now this V here is liquid velocity, this E is electrostatic, is field intensity in volts per centimeter actually. Now, usually you don't like to work in potential. If you have liquid velocity, maybe you would like to, liquid flow, you would like to connect this to the electrical current. The equivalent is you you pass current through the liquid, and this current generates a liquid flow. So in order to do that, you have to connect the electrostatic potential to the resistivity, and this is the Ohm's law, which is the potential divided by the current is equal to 1 over the resistance. Now, the resistance here, the resistance, which is equal to 1 over the conductivity. Now, 1 here is the conductivity. Now, why we don't work with resistance, we work with conductivity? This is just historical electrochemistry. People measure the resistance of wires, but then they measure the conductance of liquid. The equipment which you use to measure the electrical properties of liquid is called conductometer. The equipment which you use to measure electrical properties of wires and bulk metals is called resistance meter, right? Ohm meter. One is just the relation between the resistance and the conductivity is one over the other one. Now, the resistance in this case is going to be the sum of the conductivity, is going to be the sum of the specific bulk conductivity and the specific surface conductivity. So when you apply voltage, there is going to be a current through the bulk of the capillary, and then there is going to be a current on the surface of the capillary. They have conductivities are a little bit different. So when you put all of that in this formula here, just replace the field intensity with the formula for the resistance and the conductivity. You have this relation between the flux of the liquid, the current that you pass through the capillary, the bulk and the surface conductivity. The bulk conductivity is a property of the liquid. The surface conductivity is usually a property of the capillary. And all those parameters, which are gauge zeta potential and viscosity. So this is the formula which allows you have measurable parameters. You can measure the zeta potential of the capillary. You know the viscosity of the liquid. You can measure the conductivity of your liquid. This term is a little bit trickier. Hopefully sometimes it will be small, the surface conductivity. Or you can just measure the conductivity of the capillary together with the liquid inside. And this is the current. So this is the relation which gives you the dependence between velocity and current. The amount of liquid that moves and the amount of electricity that moves. The passing of electricity leads to the passing of liquid. And you can also see how different parameters affect that. Now, the higher the conductance of the liquid, the lower the velocity at a certain electrical current. Now again, let's announce the next award for fast thinking. Now, this means that your mobility of the liquid, kind of system for moving liquid, is going to be more efficient when you have higher electrolyte concentration or lower electrolyte concentration. Which liquid is going to move more efficiently, faster? Really? Lower. Okay, sorry, Captain, you don't get the award this time. No, the point is, the more electrolyte you have, the higher the conductivity of the liquid, right? The higher the conductivity of the liquid, the lower the speed of the liquid when you apply current. And physically, this tells you that when you have more conductive liquid, you spend more current just conducting electrons to the liquid instead of moving the liquid with respect to the capillary. So electroosmotic pumping works better when you have lower conductance liquids.
That's sort of like wash over because you're applying a voltage.
Right.
You're not applying current most of the time. So given voltage, then like, you have to apply higher voltage to get higher current, and then you
right.
Yeah.
So where your totally actually is what happens with the power that you dissipate.
Yeah.
Now in order to, okay, this tells you in order to apply high current, you need to apply higher voltage, of course, like by Ohm's law. So this means that if you want to move, let's say, salty water with the same speed as deionized water, you have to apply higher power. So at a certain point, this power is going to be so high that the water is going to start boiling. And this is where your electroosmotic pump is going to start working. Stop working. It's going to be overheated. So essentially, the more conductive the liquid, the less effective your pump, until you reach the moment when the current goes to heating up so much that it boils. So that's why electroosmotic pumps, which are one of the basic pumps on chips, are more effective when you don't have higher conductance liquid, when you don't have much electrolyte. And now kind of the basic, kind of the most important slide, let's say, like from something that you have to remember. Now, we're going to discuss the streaming potential a little bit later on, but if you just have hydrodynamic pressure on the two weight ends of a capillary, the liquid is going to move parabolically. If you apply potential across a capillary, the liquid is going to move with a plug flow. Now the question is, what happens when you kind of close the capillary? Let's say you close it like that, you put two electrodes here, and you apply the voltage. Now these two cases here are just drawn, so you can kind of like understand what happens here. And when you close the capillary, when you apply the voltage, now there is going to be this electroosmotic flow in this direction, right? But because the capillary is closed, this liquid is going nowhere. It has to return back. So you have this flow is going to generate hydrostatic pressure, which is going to generate reverse current of liquid, flow of liquid. Now this flow of liquid is going to be parabolic. Now to kind of sum up what's going to happen, this is when you sum, so this is the plug flow in this direction, this is the parabolic flow in the other direction. When you sum up these flows, you're going to find out that the liquid in the capillary is going to move like that. So it moves in this direction until this thickness, which is known to be calculated to be 0.70 times 71 times the radius of the capillary. And then it's going to move in this direction here. So believe it or not, what you're going to have in this capillary, just think physically. If you have a plug capillary and if you apply voltage, the liquid next to the walls is moving in one direction, the liquid in the middle is moving the other direction. So you have the capillary in which two liquid flows are going like that. Now why am I telling you this weird phenomenon? Because this weird phenomenon is the source of the major experimental error in electrophoretic measurements. And this is the basic thing you need to know if you are ever going to do electrophoresis. Now in electrophoresis, of course, you have to have a suspension of particles. Now what you really care is how fast the particle is going to move. However, you have to put this particle in some vessel. This vessel, however, also generates electroosmotic flow. If you just take a vessel and you put two electrodes, the liquid is going to start circulating around the vessel. Now then, if you put the particle is going to get carried by the liquid flow, right? So what is the only way into which you can measure the true electrophoretic mobility of the particle? Another chance for quick, kind of fast thinking response. What is the only way into which you can take a capillary, plug the two sides of the capillary, because there is no other way you can work, put in a couple of electrodes, put in a suspension of particles, and just measure what is the true electrophoretic mobility of the particle. Right. The only true case where you can measure the particle is when the particle is situated in this plane here, where the liquid velocity on the average is 0. This is called the stagnant layer. So if you have a capillary, any type of vessel, the moment you apply voltage, the liquid is going to start moving around. It's going to be moving in one direction close to the walls, and then because it has to return, it's going to move in the other direction in the middle. Somewhere between the walls and the middle is going to be a layer where the liquid is not going to move, just because it's in the middle of the two flows going in the different direction. This is called the stagnant layer, and this is the only case where you can measure velocity of particles through electrophoretic mobility of particles. If you measure everywhere else, what you're going to measure is you're going to measure either the particle velocity plus the liquid velocity, or the particle velocity minus the liquid velocity. So that's why if you do electrophoretic mobility measurements, which traditionally are done like that, you have a capillary, let's say here is your plus and minus charges. You have a microscope, you illuminate, you apply the voltage, and you see how the particles move. The only way you can measure true mobility is either measure it here or here in the stagnant layer. Now, this is not the usual case in many colloid laboratories. People buy equipment, and then some student or technician who has not studied colloid science and who has not read the manual, just puts in the cell and starts measuring. And the particles always move. They're always going to move in some direction. The point is that if you don't adjust the place where you're measuring right, you can get any type of result. And believe me, I have been to many laboratories around the world. This is the most common case is when people don't adjust properly and get all types of weird results and then throw them out because they're junk. And the real case is that you just have to adjust your equipment so you measure the stagnant layer mobility of the particles. And the other thing you have to remember, of course, is that whatever you do, you're going. If you put a constant voltage in water or other liquid, this liquid is going to start moving. So just the idea of kind of like I'm going to have two electrodes and I'm going to put a voltage, and I'm going to apply the voltage and only the particles are going to move is implicitly wrong. Now next time, however, on Thursday, we're going to discuss the case where we can have mobility in particles in a field without the liquid moving. This is a great force which I love so much. But so far, as long as we have constant field, the liquid is always going to move. Shalini had a question.
I don't understand why the liquid would always move in one direction. Shouldn't the molecules be moving in both directions?
The liquid moves close to the wall. You have this charged layer on the wall surface.
So the liquid always, when we're talking about liquid, it always has ions inside.
Right. Well, we're speaking about ionic liquid here. If you have non-ionic liquid, if you have oil, of course, if you apply voltage across oil, it's not going to move. So everything that we speak here is ionic liquid, one that has ions inside. And of course, the typical case is water. But organic liquids also would have some ions. Now you can say, well, how many ions I'm going to have in an organic liquid? But as you're going to find out in your homework, the problem with organic liquids is that they're so little conductive that a small amount of ions can generate enormous potentials. So in your homework, actually, you have to calculate the voltage that is generated when liquid flows through a tube. For example, if you have seen when people load fuel on airplanes, they always ground the plane in the fuel carrier. The first thing they do, they ground it, and as you can calculate, actually, you're going to find out that the flow of fuel can generate enormously high potentials if there are some ions in the fuel. Thousands of volts, which can cause sparks. Kevin had a question.
Yeah. What are the magnitudes of this velocities?
Well, it depends. It depends on the voltage. It depends on the size of the capillary. But let's see if we speak in terms of pressure that you can generate, then you can go to megapascals. I'm going to give you the formulas for exactly calculation of different types of practically important objects when you go to microfluidics. Now, just another type of equipment. This is the common equipment which is used these days, electrophoretic light scattering. In this case, you don't have to count the particles moving and kind of like measure the distance. This is done by the equipment itself because you have this diffraction pattern here. So the particles kind of move from one diffraction line to the other. So you can actually measure the speed of the particles, similar to the way you measure Doppler effect, by photomultiplier. The point, however, is that even this equipment needs to be measuring in the stagnant layer. So the first thing that you ever have to do if you ever come across such equipment is to check out the alignment. Believe me that in more cases you're going to find out that it's misaligned, especially in academic cases where you have some equipment which may not have been under proper supervision. I mean, you have to be careful about the stagnant layer. On the other hand, you can use the mobility of the liquid for something useful. Let me give a few examples. Any questions so far, by the way? Yes.
Will the position of the stagnant layer change with the?
No, it's always constant.
It's always constant.
The lucky thing, and that's good. The lucky thing is that regardless how fast this speed is, this velocity here is, so it's going to change if you change, let's say, the properties of the surface, or if you change pH or the ionic concentration, it's going to change. But this is just purely hydrodynamic calculation. This layer of liquid has to come this direction, the other one has to come this. So it's always going to be at 0.71 times the radius of the capillary. So it's purely hydrodynamic calculation. So luckily you don't have to calculate that. And here are some examples of just electrophoretic mobility measurements, zeta potential. This is some small particles from ferric oxide. Now what happens here, and what is pH equal to 6.6 or something like that? You have, this is the measurement. So what these people have done, they have put these particles in electrolyte solutions at different concentrations of electrolyte, and they have measured the electrophoretic mobility. And they have recalculated the zeta potential. This is 0, this is positive, this is negative. So what is this point called? Right. This is the point. The particles are positively charged at low potentials. Because they have OH groups, they can recharge. So they get to be negatively charged at high potentials. And you can see how fast and easy you can measure isoelectric points. Same with proteins. The problem is that you can't observe the proteins, so you have to do special types of electrophoretic measurements with proteins. You can see also that the lower the electrolyte, the higher the potential, just because you don't have that much suppression by the counter-ionic atmosphere. The more electrolyte you put, the lower the potential, because you dump all these ions into the stagnant layer. Just another example. What happens when you have some particle of constant charge, minus 60 millivolts, and what happens when you start dumping different types of surfactants, starting from one with long chain and going to one which is essentially just electrolyte. When you just have electrolyte, the potential decreases when you dump too much electrolyte. Now, when you have surfactants of opposite charge, why do this decrease and go to the opposite charge? And why is this dependent on the length of the surfactant chain? So you have negatively charged particles to which you add positively charged surfactant.
The longer the chains, the greater the distance is from the, like the greater the particle, the bigger the particle looks.
No,
So
what
it's-
is? No. It's kind of no. It's. I mean, the longer the chain. I mean, the longer the chain. What happens when you have longer chains of surfactants?
More viscous or slower flow.
No, in terms of absorption.
Longer chain.
These are likely to be hydrophobic particles. So the longer the chain, the stronger the surfactants absorb on the surface. And when you absorb too much surfactant on the surface, because the surfactant is positively charged, you have more surfactant than the negatively charged group on the particle surface. So the surfactants actually reverse the potential of the particle because you bring so many positive charges to the surfactant compared to the one on the surface charge of the particle. This phenomenon is called recharging. If you do the practical experiment, you are going to find out that you have stable suspension of particles. You add some surfactant, and what's going to happen here? At 0 zeta potential. Right. I mean, you don't have charge on the particles, they aggregate. Then you say, okay, I mean, I've done this my job well, let me add more surfactant, so they aggregate even better. And you add more surfactant, and you suddenly find out that the particles disperse again. So eventually, if you want to precipitate particles using surfactant, you have to be careful how much you add. If you add too much, they're going to redisperse again.
But can we go from aggregation to redispersion?
Yeah, in this case, you probably can, because the particles are also protected by steric coating of the surfactant layer. So they are not going to aggregate irreversibly. In the case of surfactants, so that, I mean, you have also steric interaction. The point is that, I mean, you're going to have this point of zero charge where they're going to precipitate. Okay, any questions? Okay, just a couple of slides finishing here for the reverse case. Now, we discussed what happens when you put electrodes and apply voltage, the liquid falls through the capillary. Now, then the question is, what happens if we put the electrodes, but instead of applying potential, we apply pressure here, and then we measure the, okay, it's a character, you just measure the potential between the electrodes. And what happens is, because the liquid falls, it's going to carry away the ions that are next to the surface of the capillary. So you're going to kind of, in a way, carry one type of ions from this vessel to the other one. And the bottom line is that you're going to generate a voltage. So if you remember, when we put in voltage, we generate current of the liquid, flow of the liquid. If we have flow of the liquid, this flow of the liquid generates voltage. Kind of the effect is reversible. This effect is called streaming potential. I have given you the basic formulas for derivation of the streaming potential here, but we don't have time, and possibly it's not necessary to go through this right now. You have a very simple relation between the electrical potential that you're going to generate, the pressure, the conductivity, zeta potential, and viscosity. So it's in effect the reverse formula of the one that we studied. It's derived by a number of complex calculations, integration, and so on. But the formula itself is simple. Now, what can this be used for? You have a small device. You want to measure the current in this device by some clever method. If you put a couple of electrodes, you can have in a way a sensor for liquid flow. Now, this sensor has to be calibrated, but you can measure the flow of liquid by measuring voltage. Okay, and in the last slide, I have just summarized everything that I told you so far and all the formulas. We have a time for a couple of questions. Yes, Daniel?
So this last phenomenon is that the same reason why you get a charge build up when you pump the gas?
Right, right. So, in principle, you can pump gas by applying very high voltage and the gas is going to fall through the tube. But you don't want to do this for obvious reasons. So you use mechanical pump. However, when you pump gas, just because the gas falls through the holes, it's going to generate voltage, and the gas does not have much charges inside, right? However, these formulas, you see, like, I mean, all those formulas are dependent on the conductance. If you have very low conductance here, you're going to generate high voltage. And you know the hydrocarbons have very low conductance. So you can generate very high voltage by just flowing organic liquid through a hose. And of course, that's why people ground planes before loading them with fuel and so on. Now, all those phenomena are very useful, and we're going to discuss in different types of on-chip phenomena. You apply voltage, the liquid moves. Or the liquid moves. How do you measure liquid flow on such a small scale? You put a couple of electrodes and just measure the potential that's generated by the moving liquid. And to discuss some tricks of how people can increase the pressure of the liquid and so on when we go to microfluidics. And of course, this is the basics of all measurements that you do for electrophoresis in your lab. And you can see that this is very useful. You can immediately determine isoelectric point. You can immediately determine surfactant absorption. So it's a useful instrument. It's a pity that we don't have one readily available in our department. But it's a useful instrument as long as somebody aligns it to the stagnant layer. Okay, we're finishing. So if you have any questions, you can drop by and ask now.